welcome you to my lecture today. Of course, I actually finished the material for yesterday in my recording. So the recording has already been published, and I also want to use this opportunity to say that the statistical table, normal distribution, and the incomplete gamma has already been published. You can check the canvas for access. Okay, so this morning we are actually going into something else. We are still on continuous probability distribution. Yesterday we actually visited members of that distribution. I walk you through the uniform and the normal distribution. And of course, I discussed the normal approximation to binomial in my recording, so which I will advise that you should watch. Okay, so today we basically are going to walk through three distributions. Okay, in fact, they're going to be four. I'm going to mention another one briefly. So number one, exponential. I'm going to talk about gamma. They mention chi-square distribution briefly before we go to beta distributions. Now, all these distributions, they are all classified under continuous probability distribution. Okay, so in the outline, of course, that is what I want to do. I'm actually going to walk you through some illustrative example. I'll first start with exponential distribution. Okay, now the exponential distribution and the gamma distribution, they have relationship, just like the same way geometric and negative binomial has relationship. So because exponential is a special case of a gamma distribution, then I would like to start with the exponential. Okay, so exponential distribution is actually, like I said, a member of a continuous probability distribution. You can see the density function, the f of x beta equal 1 over beta, exponential raised to the power minus x over beta. If you take a look at this distribution, it's a very distribution for modeling time before the occurrence of an event. I'm going to say again, if I actually want to figure out whatever we use, whether electrical components, we are not going to use them forever. Okay, there's going to be a time that they're basically going to stop functioning. So the question now is, how long am I going to wait until a particular component, okay, actually stop functioning? So if you want to talk about waiting time, okay, if you want to model waiting time, we're actually going to use the idea of exponential distribution. So the x that you see, okay, x will actually represent the numbers of time you're basically going to wait until that particular component, is no longer functioning. So the parameter in the distribution is what we call that beta. That is the shape of that distribution. Okay. Now, and you can see the beta has to be greater than zero. It has to be non-negative. Okay. Now, you can take a look at the example of find k such that the f of s equal to that is a legitimate density function of an exponential distribution. Okay, so when you want to, work on stuff like that, give me one second, and what I'm basically going to do I believe those of you online can see my whiteboard. Can you confirm if you can see my whiteboard? Because I'm going to write something on the board now. Can you see my board?
Yeah, we can see the whiteboard. We
Okay,
can't see
thank you
the
so.
slides anymore.
Yeah, the big whiteboard. That's what I'm saying. Is that what
Hmm.
you're saying, right?
Yep.
Okay, thank you so much. Okay, so we I told you the other time, we if I really want to show whether any continuous probability distribution is legitimate, or what we just need to show if it is continuous, okay, we need to show that this is going to be equal to one, okay, from that to that. Okay, this is a general formula, okay, but we're still going to make use of the state space. What we're going to use here actually depends on the state space of that particular distribution. Right now, you're talking about the exponential distribution. Okay, so it is from 0 to infinity, okay, and 1 over beta exponential raised to power this dx. Now, if this is a exponential distribution, okay, uh, is it 0 to infinity the state space? Because when we write that, it is s greater than 0. If you look at the way I actually specify that, okay. Now, if I can show that this integrate to 1, okay, if I really want to show that integrate to 1, okay, 1 over beta is actually constant, 0 to infinity, exponential raised to power this guy, the x. Okay, so 1 over beta. Okay, when I integrate this guy now, I'm actually going to have this, okay, divided by 1 over beta. Okay, so, and of course, this guy is going to cancel that guy, and I'm actually going to have from 0 to infinity. So by the time I actually plug in, okay, by the time I plug in that, okay, I'm actually going to have, if you take a look at this guy now, when exponential is raised to power negative infinity, okay, if you want to consider the rate of decay, like in physics, you have when something is disintegrating, something is decaying, exponential is power negative infinity is going to be zero. Okay, so this guy here now is going to be zero, right? And if that guy equal to zero, this is exponential raised to power zero, and anything raised to power zero is going to be equal to one. So here, negative negative, so that is basically one. Okay, so that is to show that the exponential distribution is actually a legitimate probability function. Now, when you take a look at the example that I was referring to the other time, okay, they gave you f of x, okay, you are actually given f of s, okay, the f of s was equal to k, okay, exp, okay, negative 2013 x, okay, you are actually giving this guy now, and they said, find the values of k, okay, for which this is a legitimate PDF. So what I expect that you should do here is basically, okay, 0 to infinity, okay, k. I can simply write just e raised to power this guy here, okay, ds, okay, equal to 1. Okay, so I'm going to integrate this guy now, then I'm going to solve for k. Does that make sense? So that is what you actually, so you want to solve for k, you bring a k out, right? Integrate this guy. I'm actually going to have this divided by this from 0 to infinity equal to 1. Okay, you plug in infinity, you plug in 0, then you can actually solve for your k. Okay, that's exactly what that question is talking about. Okay, we can give you stuff like this in whatever distribution, and ask you to figure out what the values of the constant is going to be, for that to be a legitimate PDF. Okay, so I'm actually going to go back to sharing my screen now. Give me 1 second. Okay, those trying to confirm if you can see my screen. Can you see my screen now?
It's loading. We should see it in a
Oh,
moment.
it's loading. Oh, okay. So when it's loaded, let
Got
me
it.
know. It's loaded. Oh, got it now, right? Okay. Thank you so much. Okay. Now, that's about that one. I'm gonna go to the next one. Take a look at this example. Suppose that the time in hours required to repair. I told you. Whenever you want to figure out the amount of time you're gonna wait before an event take place, you basically, if you're focusing on just the first event or one component, that is exponential. Okay. Let me just take it from here. If it is not first event, if it is more than one event, then that's going to be gamma. Does that make sense? So I'm just going to take it from there. So the moment you understand the exponential, you're basically going to understand gamma. But we're still on exponential now. Okay. Suppose that the time in hours required to repair a heat pump is a random variable x having an exponential distribution with parameter beta equal to 1 over 2. Let me tell you this. Uh, when you have an exponential distribution, of course, the parameter is beta. Okay, that very beta needs to be known. Okay, here now, you've been given to be 1 over 2. Now, look at the question. What is the probability that at most 1 hour will be required? Okay, at most 1 hour will be required. Okay, it means you basically want to figure out the probability of S, the probability of S less or equal to 1. When I say at most, I must not go beyond that particular value. Okay, 1 hour will be required to repair the pump on the next. What I'm actually going to do here is to go from, you can see, I'm actually going to end up in one, right? When I end up in one, and what is basically going to be, don't forget, in exponential distribution, the S is greater than zero. So which is more or less like going from zero to infinity. So here I'm actually going to start from 0 to 1. Okay, then 1 all over beta. Okay, don't forget this, the x, and of course your beta has already been given to be half. So all what you're just going to do is to plug the values of the beta in, integrate that, then use the range of 0 to 1, then you're done. You're going to figure out that probability. If you go to the second question, what is the probability of at least 2 hours? At least two now is going to be probability of s greater or equal to 2. Okay, s greater or equal to 2. So with s greater or equal to 2, you're basically going to start from 2 and you're going to end up in infinity. Don't forget, it's like at least 2, starting from 2 to the upper bound. When s is greater than 0, you're going to get to the upper bound. And of course, you're actually going to use this guy right now. So you are using, if you really want to figure out efficiently the probability in a stochastic world, you need to be using an appropriate probability distribution. Okay, the appropriate probability distribution for that is exponential, and that is why we actually base our inference on that. Okay, so another thing I want to talk about this exponential distribution is that the mean and variance. And I told you the other time, okay, why am I interested in the mean? Am I interested in the variance? You want to repair a pump, right? You want to repair a pump and you want to figure out, the waiting time before that very pump can be repaired. Of course, in a stochastic world, okay, that very time is going to be a random variable. And therefore, when you have a random variable, then we normally want to figure out what is the average. And that is why we need the mean. And the moment you figure out the average, then we need to tell how reliable is the mean by actually looking to figure out what we call the variance. Okay, so what I'm trying to say now, when you have an exponential distribution, okay, so when you have an exponential distribution, okay, When I have, I mean, we normally write it this way: X follow expo. I can just write this and put, you know, days. I can put whatever. Okay, it is not all the time that I'm going to put beta. It could be lambda, it could be whatever. Okay, so but I'm using beta now. Okay, so the f of x, okay, is 1 over beta exponential raised to power this guy, s greater than 0 and the beta greater than 0. Okay, so what I'm trying to say, expected value of x, okay, if you take a look at what I'm displaying now is beta. Okay, the variance of x is actually beta squared. Okay, now how are you going to derive that? Okay, what you're going to do, you're going to use the idea of how do we actually obtain the expectation of a random variable if the random variable is actually continuous in nature. So for instance, it's going to be expected value of x. Don't forget, we know this is the formula that we have, f of x dx. But right now, I'm actually going to consider the state space of the distribution under investigation. So I'm actually going to have x. What is the f of x? 1 over beta exponential raised to power this dx. Okay, now what you're going to do now is to basically integrate that. Okay, but before you integrate that guy, you need to first simplify. There's a lot of algebra that we do. Math is about algebra. So I'm actually going to simplify this guy now. Okay, if I want to simplify that guy, I'm actually going to bring out 1 over beta. Okay, this is 0 to infinity. Okay, x exponential raised to power this. Okay, dx. Okay, now when you have something like this now, what you're going to do, I know you're going to use, there's a rule that we call integration by parts. I know, so you've come across that in the high school, but you know what I'm going to be using. I'm actually going to use the idea of a gamma function. Okay, if with the idea of a gamma function, you're basically uh, going to be fine. Okay, I'm going to show you now. Okay, how the gamma function work on this. I'm not talking about gamma distribution now. I'm talking about gamma function. The idea of a gamma function can actually be used to figure out the antiderivative of that look like this. Don't forget there's a function of x here. This is another function of x. So let me just say, let me just write gamma function. Okay, you know, gamma function. If I have a gamma alpha, the gamma alpha is 0 to infinity, x raised to power alpha minus 1 exponential raised to power x dx. Take a look at this. This is a gamma function. Okay, so this is integral definition of a gamma function. Okay, if you don't notice something here, when this is coming alpha minus 1, this is going to be gamma alpha. Okay, it's going to be equal to the non-integral. The non-integral is going to be alpha minus 1 factorial. Okay, when I have a gamma alpha, okay, defined as this, okay, that is going to be called alpha minus 1 factorial, okay, which means if, let's say I have 0 to infinity, I have x raised to the power 6, this dx. Oh my God, if you use the integration by parts that you learn in high school, it's going to take forever without gamma function. Okay, now if I want to apply the idea of a gamma function now, what I'm actually going to do, this is gamma 7. This is gamma 7. And what is gamma 7? Gamma 7 is 7 minus 1 factorial. That is 6 factorial. I'm done. That's super easy. Okay, so the gamma function is, if you understand the idea of a gamma function, something like this can easily be achieved. But let me tell you this: before you can apply the idea of a gamma function, you got to make sure it is from 0 to infinity. If it is not, then gamma function cannot be applied. Now, I quickly want to figure out this guy now. Now, can we write this as a gamma function? The way it is, let's compare this and this right now. There's an s, right? There's an exponential carrying negative s, but this is carrying x and raised to power beta, so which means something needs to be done first. Okay, I needed to look up now. You're gonna see the way this is going to be. Let me clean this. Okay, so if you take a look at what I have, okay, the expected value of x, okay, equal 1 over beta is 0 to infinity x exponential raised to power this ds. Okay, so what I'm going to do now for this to suit a gamma function, I can let y be equal to this, okay, because I want exponential to carry the variable in the here, exponential is just carrying a variable, right? But here it is carrying a variable and the parameter. Okay, so I'm going to use a substitution method. So here this imply my x will be equal to beta y. Okay, if x equal to beta y, I can no longer use the x, right? Then what is the y? The x. Okay, the y the x here is 1 over beta, and here the s is going to be equal to beta the y. So I need this guy, I need this guy, and I need this guy. Take a look at that. So if I want to write this again now, I'm actually going to have 1 over beta 0 to infinity instead of x. Instead of x, I'm actually going to have a beta y, and here I'm actually going to have this guy instead of the s. I'm actually going to have beta the y. Okay, now if that is what I have, so this cancel this, right? And if you cancel that, there's a beta here, right? I'm actually going to write beta 0 to infinity y exponential raised to power this. Oh my God. Take a look at this guy in the parentheses now. This is a gamma function. And what kind of gamma can we call this? This is going to, because this is going to be raised to power 1, right? And if this is, that is going to be gamma 2. And what is gamma 2? That would be 2 minus 1 factorial. So this guy is going to be 1 fact 1. So 1 times beta. So it's basically, I'm actually going to have this, which is equal to beta. So right now, I've succeeded in deriving the mean of the exponential distribution. Any question? Okay, so you can actually go the same way, deriving the variance. Don't forget, you want to derive the variance. Okay, if you want to derive the variance, you actually need the information. Okay, you know that the variance of x is expected value of x squared minus expected value of that. So we've already, you've already figured out this guy now. So that is beta squared. Then you actually need this guy, so you can proceed the same way. Okay, 0 to infinity s squared 1 over beta d divided by the x. Take a look at that. So if you continue with the way I actually, do that before, you basically, in the end, I'm afraid, I think this is going to give you 2 beta squared. So that when you then with that, so you're actually going to have 2 beta squared minus beta squared, and that will give you beta squared. Okay, so if you follow that, so that is how the mean and the variance of the exponential distribution is actually going to be derived. Okay, so I've already done that. Derive the formula above. I'm referring to what I've done. Okay, then to take to repair a 8 point of this type, and they say, how long do you expect? Expectation is the mean. Anytime they say, do you expect? Or what you're just going to do, what does it mean? The mean is beta, right? We derive the mean to be beta, right? So beta, that is now so you just equate that to what they give you as the values of the beta. Okay, that is the time you actually going to wait. And look at 6.4. If an exponential distribution has a mean of 2.5, what is the standard deviation? Is that not easy? Okay, if the mean is 2.5, the mean is beta, right? The variance is beta squared. The standard deviation will be beta, because the square root of the beta squared. So which means the mean and the standard deviation, they're going to be equal. Does that make sense? Okay. Now you can try 6.25. You can try 6.25. So that's basically going to be easy. Okay, so I think I'm done with the exponential distribution. I want to go into gamma distribution, but let me tell you this: the same relationship that the geometric and the negative binomial has. Okay, exponential and gamma also have the same relationship. Okay, in exponential, just trying to figure how, how long am I going to wait before the occurrence of the first event. But the gamma is now going to say, how long am I going to wait before the occurrence of not just first, because we're going to generalize that gate event. Does that make sense? The numbers of events is going to be more than one. And let me tell you, the gamma distribution is going to have one additional, one parameter more than the exponential. Okay, the exponential has a parameter beta, right? Have a parameter beta. Then for the gamma, we're going to introduce alpha. Okay, we're going to introduce alpha. So the parameters of a gamma distribution is basically going to be alpha and beta. Okay, what is the alpha? The alpha here is just telling you the numbers of such events. Situation where the alpha equal to 1, you are back at exponential. Okay, now, but for you to be able to understand a gamma distribution, you need to first understand the gamma function, which are for function now. Okay, so because why do we need gamma function? We basically need gamma function, in case we basically want to figure out, something that has to do with integrating, the product of two functions, and in such a way, that the state space is from 0 to infinity. Okay, so this idea we actually be used in figuring out some complex, function in exponential distribution, and also in a gamma distribution. So, like I said, I want to introduce you to what I call gamma function now. Okay, so we got two definitions of gamma function. Okay, we got integral definition and the non-integral definition. Okay, so if you take a look at this guy now, so this is an integral definition of a gamma function. Okay, so if I have a gamma alpha, okay, it can actually be expressed as that. Okay, so where your alpha is going to be greater than 0. Okay, so if you take a look at that, what of in a situation, if I have um maybe x raised to power 6, okay, and exponential raised to power negative x, okay, and the x, okay, and of course the state space is going from 0 to infinity. Okay, so this is basically going to be called gamma 7. Okay, so take a look at that. So instead of me to go through the rigorous method of integrating by part, that's basically going to take forever if the power of x is more than 1. Okay, provided we got a state space of 0 to infinity. Of course, we can securely write this as a gamma 7 if there's a 6 here. Or what you're just going to do is to add 1 to that, and that become gamma 7. Okay, and if that is gamma 7, we can actually use the idea here. Okay, gamma n equal to n minus 1 factorial. Okay, so this guy is actually non-integral definition of a gamma function. Okay, so the non-integral definition of a gamma function can actually be equated to the integral one. Okay, so what I'm trying to say now, so I can actually equate this guy, okay, to what I'm going to call alpha minus 1, okay, factorial. Okay, so the same thing here, gamma 7 going to be called 6 factorial. Okay, of course, we all know what 6 factorial means. Okay, 6 times 5 times 4 times 3 times 2 times 1, and of course that is basically going to be very easy to figure out. Okay, so among other properties of a gamma function, okay, is this, though gamma alpha can be written as that. So what I'm trying to say, that is going to be kind of recursive. Okay, gamma 7, okay, can also be actually written as what I'm going to call 6 gamma 6. Okay, so and you can also go all the way where I can have 6, okay, multiply by 5, gamma 5. Okay, this something is going to continue, that way. Okay, now another thing that I actually want us to know is the fact that, gamma 1 is going to be equal to 1. Okay, gamma 1, okay, gamma 1, is if you want to take a look at this, so this is going to be called 0 factorial, right? That's going to be called 0 factorial. And of course, you all know 0 factorial equal to 1. That's how been derived to be equal to 1. Okay, so because of that, so we're going to say gamma 1 uh, is basically equal to what I have. Okay, so right now. Okay, so the next thing I'm basically going to consider, gamma half. Okay, if you have a fraction, okay, gamma half is going to be square root of pi. I need you to take note, okay, of that. So when I want to talk about that, this is what I'm going to this is what I'm trying to talk about now. So that has already been proved. Okay. What of in a situation, okay, where I got gamma 3 over 2. Okay. So what of gamma 3 over 2? So what am I actually going to have? Okay. I can actually use the fact that gamma alpha equal alpha minus 1, gamma alpha minus 1. So what I'm basically going to do here, so which is going to be half, okay, gamma half, okay, and you know what, I can now write half, okay, and what is gamma half? That is going to be square root of pi, okay, so this is going to be square root of pi, okay, so the same thing, you can also, what of if you are given gamma 7 over 2 now, okay, the gamma 7 over 2, if you subtract 1 from that, you're basically going to have, 5 over 2, okay, gamma, okay, 5, okay, over 2. And that is going to continue all the way because you basically want to get down to where you're actually going to arrive at the gamma half that you can actually, substitute square root of pi. So I'm going to continue, to go until I got to what I need. Okay, so if you take a look at this, this can go again, subtracting 1. So you're actually going to have 3 over 2, okay, gamma 3 over 2, okay, and of course if you take a look at what I have now, so I'm actually having, okay, 5 over 2, okay, 3 over 2, and of course this guy here you can actually go into half, okay, uh gamma half, okay, and by the time you multiply all of that, so you're basically going to have 15, okay, over 8, okay, and the gamma half is basically going to be square roots of pi. So take a look at that, okay. So the gamma function, we actually make our computation, that initially look complicated, to be easy, to do. Okay, so I'm actually I'm gonna erase that now. Okay, now if you look at example 6.19, of course, you can actually, without your calculus knowledge, you can really figure out, you can really figure this out, using your gamma function knowledge, you can figure this guy out. And when you take a look at example 6.20, let x be an exponential random variable with a parameter, okay, beta. Okay, so what I ask you to do now is to derive the cumulative density function. Okay, now if you want to derive the cumulative density function, of course, what you basically are going to do, okay, is to use the idea that I use okay. I think I will first, like, let me do some other explanation. Okay, so that's because of the fact that the moment you understand exponential very well, you're basically going to understand the gamma, because the gamma is just going to be a generalization. You get what I mean? Okay, now let x be exponential random variable with parameter beta, derive the cumulative. You remember the other time we actually talk about the cumulative, right? We talk about cumulative. We talk about cumulative. Okay, we talk about cumulative distribution function. Okay, now f of s is 1 over this exponential raised to power this s greater than 0, that, and I want to get a CDF. Please take note, the two are not the same. Okay, the PDF is lowercase, the CDF is an uppercase. And what is it talking about? I want to find this, which means I'm basically going to go from 0 to x. But now f of t, the t, okay? You remember the way we used to do it? Okay, so right now, so 0 to x, 1 over beta, this guy, okay, the x. So 1 over beta is 0 to x. Oh, sorry, let me be using t instead of, I've already defined that because of this x. Okay, so exponential raised to power this, the t. Okay, so when you do that, you actually gonna have this divided by 1 over beta from 0 to x, right? Where we did it the other time. And this guy is going to cancel that guy. Okay, so when that guy cancel that guy, so what is going to happen? So we're going to see now. So what is going to happen? We're basically going to have the CDF, which is this guy, let's say equal to that, to be equal to negative exponential this over beta from 0 to x. So this is going to be negative this x, okay, minus into minus 0 that. So, and this is basically going to be this plus 1, so which is 1 minus this guy. Now this is the CDF that we talk about. Okay, if this is the CDF, okay, now this is going to tell you that you're going to wait until x. What about more than x? If you want to talk about more than x, that's going to be complement of this, which is for more than now. Like if I want to talk about in survival analysis, you basically want to know, okay, whether the patient will survive, patient with a terminal disease, whether the patient will survive more than a particular period. Okay, in that situation, you basically want to find this, okay, which is going to be 1 minus this. And this guy is a CDF. So if that time follow exponential distribution, it's going to be 1 minus what we just derived. It's going to be 1 minus what we just derived. Automatically, this is going to be that, right? Take a look at that. That's going to be that. Okay, so I think I put some other questions, 6.20. Find the evaluate the probability of s lie between 0 and t, evaluate the probability of s greater or equal to that, find m, so you can investigate that. But before I'm going to go to gamma again, uh any random variable that follow exponential distribution, we have a memoryless property. I think I want to discuss that. That's very, very crucial. Okay, if a random variable follow exponential distribution, it's going to have a memoryless property. Now, what do I mean by memoryless property is I'm actually going to use an example from a store. If I have a store, I'm waiting for customers to come. Of course, stores used to be happy when customers come around. Okay, so when I get to my store and actually wait until time T, okay, and maybe customer didn't arrive, and I continue to wait, the distribution is going to be the same. It doesn't really matter whether So what I'm trying to say that if you wait until time A, okay, and until customer arrive, and customers, you have not seen any customer arriving, and you continue to wait, the distribution is going to be the same as when you start. Does that make sense, right? Okay. Now, memoryless property. Okay. Now, in the memoryless property, okay, the probability of s greater than x plus a, okay, given s greater than a, okay, is the probability of s greater than that. That's exactly what we mean. Okay, the conditional probability of s greater than s plus a, okay, given that s greater than a, okay, I told you you didn't observe any customers until time a, okay, and when you continue to wait, okay, the distribution will be the same as when you started. Now, if I want to show this guy now, we're basically going to use the idea of A given B, oh my God, which is going to be A intersection B. You remember we've done that, right? We're going to use the idea of this to figure that out. Okay, so this is an event, this is another event, right? Okay, now what we're going to do now is deriving that. We're going to derive that now. Okay, so uh, if you take a look at that now, the probability of x greater than x plus a given x greater than a, okay, we're actually going to be s greater than x plus a, comma s greater than a divided by s greater than a. Okay, we're using this idea, right? Right? That's what we're using. Okay. Now, when you take a look at that now, okay, what is common? What is the intersection between this guy and this guy? It's going to be this guy. Okay, that is it. They have this guy in common. S greater than s plus a is nested inside s greater than a. Okay, so this is going to be equal to s greater than x plus a divided by s greater than a. Okay. Now, if you take a look at this, that's a survivor, right? Survivor more than, right? You know, the other time I said more than, right? Okay. Now, if I want to get it using the idea of a CDF, so this is going to be the same as 1 minus x less or equal to x plus a divided by x less, 1 minus x less or equal to a. Take a look at that. And in that situation, I can actually write 1 minus f of x plus a, okay, in terms of CDF minus f of a, okay. And don't forget, the other time I derived the CDF, right? Okay, I derived the CDF, right? I derived the CDF of the exponential distribution. Okay, we derive the CDF, okay, the f of s to be 1 minus this, right? Okay, so what is the f of x plus a? The f of x plus a is basically going to be this, okay? Just plugging in that. Well, what is the f of a? Okay, the f of a is basically just, plugging in that. Take a look at that. Okay, now if you now plug in that here now, okay, when you do 1 minus this, so which means, okay, if you want to continue now, if you want to continue on that now, so what we want to find the probability of s greater than s plus a given s greater than a will now be 1 minus, so 1 minus 1 minus this guy now, okay, this guy now divided by 1 minus into 1 minus, that guy now. So when you take a look at all of that, okay, now you're basically going to say minus minus 1 is going to cancel out. I'm actually going to have this guy, okay, divided by this guy. Okay, now you can split the guy by the law of, you can do minus x over this minus a divided by this. Now this divided by this. So this cancel that. So what do I have now? Okay, if you take a look at that, that's what we derived before. So this guy is the probability of s greater than s, which is this. You see now, we've already proved that this guy is going to be equal to that guy. Okay, that is a memoryless property. Okay, so that is how that is derived. Now I quickly going to go into the gamma. It's a gamma distribution.